Okay, so good morning, and today's agenda is actually to do a recap of thermodynamics, and I'm assuming that all of you have done at least one course in thermodynamics, and so that's why it's a recap, not an introduction. And most courses in statistical mechanics start with thermodynamics and then go to statistical mechanics, but somehow I prefer that it's useful to have a few concrete things set up in statistical mechanics before discussing thermodynamics, so that you will appreciate what thermodynamics can do and what thermodynamics cannot do and what statistical mechanics can do. I mean, these are the few things. That's the reason I do it, in the 10th lecture rather than the first lecture. Okay, so let's sort of start with the basics of thermodynamics. So thermodynamics is based on a small set of laws that have been obtained from years of experimental observation of macroscopic systems. Okay, so it's got a concrete experimental backup. Okay, so and the state of a macroscopic system with a large number of degrees of freedom is actually specified by a small set of variables, and these are called the state variables. Again, these are terms which I've been using, and the state variables might be extensive, so particle number, volume are extensive examples, or intensive like pressure, density, or temperature. These are all intensive variables. And a state function is any function of the state variables, and it doesn't really depend on how you came to that configuration. So in some sense, in the space of state variables, you pick a point, the state function will take a unique value. Okay, there's no memory or whatever. Okay, that's what we mean. And in equilibrium, all state variables may not be independent. The equation of state, for instance, that we write for a single component ideal gas, which is PV equal to NKBT, is actually one example of this fact. Okay, so these are fairly simple statements, and are there any comments or at this point? Okay, if not, let me proceed. So we'll now discuss yes, go ahead.
So will you talk about exact and inexact differentials?
Yes and no. I mean, I'll do a little bit. Okay. Yeah. Okay. I'll do a little bit.
Okay, sir.
Mm-hmm. Okay. So the zeroth law of thermodynamics. So it says something like this: if two systems are in thermal equilibrium with a third system, then the two systems are also in thermal equilibrium. Okay, so it's a very bland statement. It doesn't look like it has any content, but actually it implicitly introduces the notion of temperature. Okay, so what you do is this third system, think of it as something which measures temperature. Okay, and it need not even be calibrated. Okay, so but it can have some meter which gives you some number. Okay, we don't know what that number is. The number need not be equal to temperature. It could be complicated function of temperature. I don't care. Okay, so that's what I mean. It need not even be calibrated. Then the zeroth law says that, so if you take that guy, third guy, and you keep it, they call the systems 1 and 2, you put it into system 1 and you get some number, and you go and once they reach and go to this other system, again you get the same number. So what does it says that these systems 1 and 2 also have the same, whatever is the thing, they have that same number. Okay, so, and we don't need to actually assign a precise number, we just have to say that they take whatever that is, they have the same value. Is this point clear? Okay, so in some sense it's like giving you a reason to define something for temperature. So but then we know a little bit more. We can let the third system be an ideal gas. Okay, and then we can assign a temperature using the ideal gas law. So there is some temperature which is got by studying your ideal gas, which you can assign to that thing. And now this is a calibrated one, unlike 2. Okay, which just uses zeroth law of thermodynamics. Now I'm using something where I understand this system. It's an ideal gas. Okay, and so you can now repeat whatever we said in 2, and then now you can actually assign a number to it. Is this point clear? So you're able to say that you can assign what we call a temperature to a system. Okay, that's all. Okay, so we can even call this the ideal gas thermometer, because its job is to only measure thermometer. Okay, but of course in real life you're not going to use an ideal gas thermometer, and you might for instance we can use mercury thermometer if you want to measure your body temperature, or there are resistors whose resistivity change with this thing, or something else. There are many examples of how temperature is measured. Depends on the system. So you could ask, how do we measure temperature at when we are doing milli-Kelvin experiments? How do we measure that? Okay, and please look it up. Okay, look up what these people do. And I just want to give a plug for this book. I had totally forgotten about this. This is a book by Tatum. He's a professor at in a University of Victoria, I guess, in Canada, and he's written a very nice book on thermodynamics, and it's freely available. But here I'm linking the link. If you click on this, magenta colored thing, it will take you to his section on the zeroth law of thermodynamics, and I think it's a worth read. It's like, I would say, a 5-minute read, and I strongly recommend that you download this and click on this thing, and of course download the whole book if you wish. And I think it's worth reading through that book. It's at a very nice, it's well done. Okay, and it's one of the books I use when I teach thermodynamics. Okay. Now we come to the first law of thermodynamics, and this introduces a state function called U, the internal energy, and to maintain conservation of energy, which is written as follows. Okay, so the so let's write this thing. We'll write this as du equal to d bar q minus d bar w, and where w is the work done by the system. Okay, and Q is the heat absorbed by the system. So the idea is that you supply some heat to the system and it absorbs it, its internal energy goes up. If the system does some work, then it loses its internal energy. So if you come back to the gas, ideal gas, and ask what is that internal energy, we know that it is the average energy of all the particles in there. But before people understood even that things were made of atoms, etc., internal energy had already been defined. Okay. Today we understand in an ideal gas what that means. Okay, but when thermodynamics was found, or whatever created, when the foundation of thermodynamics were created, they needed to have this object called U. Okay, so now comes this inexact differential, or there are many terms to this, and the whole point here is that the two terms on the RHS are path dependent. Depends on how you so you remember we defined state function to be something which does not depend on how the system reached its current configuration. Okay, so the statement here is that neither Q nor W are state functions. Okay, but you can do it infinite. It depends on what path you take in the space of state variables. The answer depends on that. Okay, and so really these two cannot be sort of naively written. So Q, what one is saying is Q is not a state function, nor is W. That's all. Okay, that's all one is saying. Okay, but U is, and so this change. This combination that we have here is something which the difference is actually exact derivative of a state function. Okay, and so the LHS, so the statement when I write D here without this thing is that it is path independent and leads to a state function. Okay, so now let's look at, we know what Q is, but what kind of dW is actually a placeholder for fairly general things. And so the work done by the system is in analogy with mechanics, where it will be force times displacement, right? So these are called generalized forces and generalized displacements. So minus Fi dxi, where there could be, I could run over all possible things. So there are two examples that we are giving here. One is which you know very well, PdV. Okay. So that is that comes with plus. So d bar w is PdV, and here I've introduced minus mu dn. Okay, so the idea here is that if mu is the energy that you need to create to change particle number by 1. Okay, so that's what it is. So the chemistry definition is probably very apt to understand. Chemical potential is that. Okay, so dW. So this is an example for a one component fluid, not fluids. Okay, so again I'll pause here for some questions, comments. Okay.
Sir, what did you just say about mu?
Sir, would it
The
be like
energy
mu1
to
dn1
create.
Mu is roughly the energy. In chemistry, it is defined as the energy you need to create one particle of whatever is the fluid, whatever is the thing, one atom or one particle. Okay.
So does that mean by giving energy you can get mu particles?
Yeah. So what we the correct way to think about this is to have the way we will think about it is not that way, but we will think about it as follows: as so suppose your system is in contact with another reservoir where it can exchange particles. Okay. And then what you will do is when they reach equilibrium, something should become equal. The analog of temperature became equal when energy transfer stopped, right? In some sense, in a thermodynamic, it reached equilibrium. Similarly, average particle number will freeze at some level, right? It'll become so that the quantity which will become equal is the chemical potential. That is what is our definition. But if you look at this mu dn, so if delta n is 1 and you think about dW as some kind of energy, right? So it just says that dW is, so you need to give up, if you want to increase the particle number by 1, you need to give up energy mu.
Yes, I understand.
That's all. Okay. So that's literally reading this. If delta n is 1, mu should, it tells you that U changes by that much. Okay.
Sir, how is it as a dn? Shouldn't it be discrete?
Huh? Oh, come on. We can do that. So when numbers are very, very large, we can treat n as a continuous variable. We already discussed this earlier in the context of, I think somebody even asked this, how are you differentiating with respect to n and stuff like that. Okay. So.
Okay, sir.
Okay. You can, if you want, replay n by v, you can do something like that and write number density if you want. Okay, you could do something like that. Okay, so now next comes the second law of thermodynamics. It introduces a new state function, the entropy, and it states that ds is greater than or equal to the heat supplied over T. Okay, so by ds, I'm talking about infinitesimal changes. So the classic case is if your system is isolated, that means it's not receiving energy from anywhere and things. So delta Q is 0. It says that that ds for any isolated system can as a function, if you keep observing it as a function of time, it will keep increasing. It's never going to decrease. It can be constant. That's what it says. ds. This is a more common version of this. ds greater than equal to 0 for isolated systems. But here I'm not saying that my system may not be isolated, and then this becomes the there is still an inequality. Okay, and okay, so this is the statement, and you can ask when is the equality obtained? It is obtained for reversible processes. Okay, so you can use reversible processes to find out what S is. So S is a state function. So if you want to go from A to point B, you try to go through it with some kind of reversible process kind of thing, and you ask how does it change. So that's how you will get you can get formula for S in some experiment. I'm talking about thermodynamics. We have, of course, in statistical mechanics, we have the fundamental postulate, right, which gives you a formula. Okay, so for a one component fluid, which is like I'm just using one component fluid for if you want, you can call it ideal gas. Okay, slightly more general statement. S is a function of U, V, and N. Okay, this is what we get. So where because U, V, and N are state variables. And another property is entropy is an extensive quantity. So if you scale U, V and lambda n by the same lambda, because all extensive variables, this will also transform with lambda. So this is just a statement. Okay. So now what will happen? So now you come back here and so you can see that so if for a reversible process, d bar q is just T ds. Using the equality here, so we can come back to this law where we have put dw is p dv minus mu dn and write for this thing as T ds, and oh god, why am I jumping so much? Yeah. So we get this what is called a TdS relation. Okay, TdS equal to du plus pdv minus mu dn. This is just writing it for a one component gas, but you can see that you can I mean for other systems also there will be the analog of first law and there will be dq, so you just go ahead and substitute for dq TdS. Okay, so and the fact that the TdS is not d of anything, right? So that is also in agreement with the fact that d of there is no state function for q. It's not d of anything. Okay. So now we'll come. I mean, there is something. Yeah, 1 second. Let me just say this statement and then you can ask your question. So the way I stated the first law, it looked like the internal energy was a fundamental. It was a state function. But while in our StatMech course, we've been always working with entropy as a crucial state function, and so I want to discuss that first. Okay, go ahead.
Sir, S is kB ln T. So TdS is just T into kB ln T. So these are both state functions. How is LHS a state function and RHS is not a state function?
Yeah, so now I'm giving you a mathematical statement. What I'm saying is, so also now independence comes. So it's a state function. T is overspecified. So S is the function only of U, V and N. T is not. Okay. You can't. So that's a conjugation. See, U and T will think of them as they are conjugate variables. V and P are conjugate variables. N and mu are conjugate variables. Like P and Q. Right? I mean, this is the kind of thing. Okay, so they pair up. Okay, so either you specify U or you specify T. If you specify T, you're working in the canonical ensemble. So in that sense, T is not quite. T is also a function of U, V, and N. This is also. So what I'm saying is that this TdS is not D of some function of U, V, and N. Okay. So yeah. So you are in a sense right that one was Cavalier here, but I also mentioned that all state variables may not be independent. So you should. So you can't, I mean, either you work with P or you work with V. You can't have both of them, I mean, for instance.
So you're saying we don't know T, so we can't use the formula Boltzmann?
No, yeah, what I'm saying is T is not a state variable. T is a state function, like S.
Sorry, here the equality.
Hello? Somebody said something, but I can't hear. Huh?
Yes, sir. In here, in second law, the equality is obtained for reversible process.
Yes. So yeah, this is this first law for we are using a reversible process to write this. So what I'm saying is for reversible processes, we can use a reversible process to figure out how S changes. Yeah. So this thing is for reversible. I mean, the process is reversible. Okay. That's what I'm assuming. So now come back. So there are two different representations. One is, well, energy is your state function. The other is entropy. And you actually have a freedom to choose what is the state variable and what is the state function. So in the energy representation, entropy is a state variable and internal energy is a state function. So U equal to U of S and other variables are there. Okay, similarly in the entropy representation, S will be a function of S will be equal to S of U with other variables. Okay, so the internal energy, sometimes instead of calling a state function, these are called thermodynamic potentials in thermodynamics. Okay, so the internal energy is called a thermodynamic potential. And why is it called a potential? Because we know that like forces come by taking derivatives. Okay, so especially this is really pakka, this thing, because if you see here, T is just du by ds keeping Vn fixed. P up to a sign is du by dv and mu is du by dn. Okay, so remember we thought of P and mu as generalized forces, and that's what is happening. So that's so this is the second term which is used. In the entropy representation, which is more natural to statistical mechanics, we of course, it's more messier, but 1 by t is ds by du, and p by t is what comes out when you take derivative of s, and mu by t is minus ds by dn. So you can see that there's a reason why people in thermodynamics liked U as the energy representation. But what is more natural from the viewpoint of Boltzmann's formula is the entropy representation in statistical mechanics. Okay, so I'll again pause here for questions. And again, I would recommend that you read Tatum's discussion on the first law. Okay, so by the way, there is a third law, and I did not write anything about it, but I'm going to tell you what it is before I move on to a little bit other things. So the third law basically says is a statement about what happens to entropy as t goes to 0. Okay, it just says at t equal to, as t goes to 0, t goes to 0, s goes to 0. Okay, what does that mean? So if you go back and look, it says s equal to, so it says omega equal to 1. That means at 0 temperature, if you hit 0 Kelvin, what you will, everything goes to its ground state. Okay, so that's the statement of the third law. Okay, so now, so you can pick any of the two representations, and the key point here is that first derivatives, we now see that it gives us the generalized forces up to some factor SP factor to get the generalized forces. Now you can ask, what about the second derivative? Does it mean anything? And yes, and this is something. It's like in we saw in classical mechanics. So the first derivative of the potential, its extrema gave you equilibrium points, and then stability was studied by looking at the second derivative. Same story here. First derivative of the potential gave you something, and then so let's look at our thermodynamic system is supposed to be in equilibrium, and so we will consider a system now consisting of two subsystems labeled 1 and 2 that are permitted to exchange energy. First, let's just do energy for simplicity. Then we can let them exchange. We can do a few more things. So extensivity of entropy says that if U is, so it says the energy has to be split between these things. So these are all state functions. So as I'm again only focusing on two variables, there can be more. Okay, so S of U V will be equal to S of U1 V1 plus S of U2 V2, etc. so on and so forth. And what is the change in entropy if we change the U, if you change this to U plus say du1 and change U2 to U2 plus du2, but now U is fixed, so du2 will be minus du1. So you put that in and you pull this out here, and by definition you go back here and look, ds by du is 1 by t, so this will become 1 by t1 minus 1 by t2 times du1. So this is, so you are given something like this. So the system is in equilibrium. So first line is just a statement of extensivity. It says that if you break it has two parts, it's equal to the sum of the parts. Okay, this is a second way of understanding extensivity. And what this says is that if you try to change the distribution in an infinitesimal way, because they are in thermal equilibrium, T1 is equal to T2, so this term vanishes. So it says that the first order change in this thing is 0. We can do okay. So that means it's an extremum with respect to this variable U1. We can do the same thing with V1, V2 also. So let's say that the total volume is V1 plus V2. So you can imagine a gas with a barrier separating them. And the things can push. So now again we'll get a similar formula, but it will be ds1 by dv1 times du1 delta u1 plus ds2. Similar thing you can
Hello?
do. Yeah.
Sir, do partial derivatives work that way? Like if dou u by dou s is temperature, then does it mean that can we say that dou s by dou u is 1 by temperature?
Because
I
that
mean,
is the...
do partial derivatives work that way?
Then you're claiming this formula is garbage, or equivalently this formula is not correct. So which formula do you not agree with? S is a state function. That means the function of these variables s, u, v and n. So ds is ds by du. I can write that, right? I can write if you change u, v and n by small amounts, du, dv, du, n, you will get partial derivatives. So
Okay,
it's a function. S is a state function, so I can differentiate. I can take partial derivatives. What do you mean partial derivatives don't work? Then you are saying that S is not a state function.
Let me rephrase it. I
Okay,
was just asking that in general, if dou y by dou x is some quantity, say x, say z, then does it mean in general that dou x by dou y is 1 by z? In general, maybe here
I'm not saying that. I'm not saying that. For one variable that is true. Right? dy by dx equal to 1 by dx by dy. You agree? For one variable. For multiple variables that's not true.
Okay.
I mean, look here. This is being said here. What does that mean?
Yeah, the others are being held constant.
Yeah.
Okay. Yes, sir.
Okay.
Okay, I get it.
So here also, if V1 is being changed, right, that will be there in the ellipsis. But that will get, so when V is changed, this will get contributions. But there, we are only looking to first order. We are not looking to second order. Okay. So if you are looking at terms which are du, dv and all, we have to worry about. Those are a different thing. So we are only looking to first order in the variables. So we'll look at du1, du2, dv1, maybe dn1, so on and so forth. Okay. So what we see is that the system being in thermal equilibrium says that 1 by temperature should be equal, so this thing vanishes. So ds total would be 0. So now let's move to look at the other terms in the ellipsis. So let's look at the V part. So now if you said V equal to V1 plus V2, let's say, and then if you're going to make changes in V1, V2 will, if you increase V1 a little, V2 has to go down. Again, we will get something. But what will come, the analog of this will be P1 by T1 minus P2 by T2 times delta V1. That's what we will get. Okay. But at equilibrium T1 equal to T2, so we also know pressure should match, right? So the volume, so if you have something which will let the barrier move, where will it stop? When the two pressures on both sides become equal, they will cancel each other and it will stop. Right? So the pressures being equal works out. Similarly, if you allow number exchange, the chemical potentials have to become equal. So the condition, and that is the condition for thermal equilibrium. But the condition for thermal equilibrium says that ds that should be 0. If you try to make infinitesimal changes in the variables, in these things, it should. So it says that ds is 0. If you try to modify things on this right hand side. Okay. So I just said here, one can let two substances because the total volume is kept with, but the individual volumes can vary. At equilibrium, the pressures agree. Again, ds total is 0. So in other words, the energy is distributed so as to, so if you look at the this thing, energy, volume, everything is distributed so as to extremize the thermodynamic potential. Extrema only, because statement of first derivative, so all first derivatives will have to vanish in some sense. So that will tell us what is the condition of equilibrium. Okay. So, but what about second derivatives? Okay, and they again, like in classical mechanics, here also these have something to do with the stability of the system. But there's a second thing that you get. So you get something called response functions. So what is a response function? It's so you do something and then it changes, right, something. And so response functions are like specific heat, compressibility, etc. These are all determined by second derivatives. Okay, there are prefactors, but at the end of the day, CV in the entropy representation is just the second derivative of S with respect to U square. Okay, and there's a minus T square, etc. And CV here is plus of T d square U by ds square. So this is in the energy representation, while this is in the the first one is in the entropy representation. These two are equivalent formulae, and you can prove these things. It's a nice exercise in thermodynamics to prove these things. But I want to mention something, is that the CV, we will see below later that CV should be greater than 0 for stability. Otherwise, what will happen, that the system can lose energy, and its temperature can keep on going down. Okay, so that's what will happen. So if CV were negative, then the system will spontaneously be able to give up energy to the surroundings or whatever. Okay, and we will see when we discuss real gases that we will find situations where things like this will happen, or compressibility, which should be positive, becomes negative. Okay, so coming back to this, T is some positive number, so minus. So this says that for CV to be positive, d square S by du square should be less than 0. Okay, so that means that this is like it should be a maximum, right? If you have one variable, function of one variable, and you are an extremum, the second derivative being negative, what does that mean? That it's a local maximum, right? Hello, is this point clear? Hello?
Yes, sir.
Okay, I thought I lost connection or something because no response. Okay, but if you look at U in this representation, you get the opposite, right? CV being greater than 0, it requires that U be, it be a minimum. Okay, so, and you might wonder why is this happening? And that is because there is if you look at how you go from U and S, if you exchange F equal to U minus TS, there's a minus sign. So if you try to think in terms of this, in terms of entropy, you maximize entropy, but in terms of energy, you minimize energy. Okay, that's what this statement is. So again, there's a chemistry thing which you would have seen. There's something called Le Chatelier's principle, which says that small deviations away from equilibrium, system will change to restore equilibrium. So this is where this is, right? I mean, this is what we are doing. I mean, there's a combined system. We are making small changes here. We are taking something here and putting it here and pushing it away from equilibrium. And the system's response will be to come back to equilibrium. Okay. So this is a statement for a function of two variables. It's actually a function of three variables. You can write. It says that, so you get a matrix of second derivatives. And so what this thing says is that the eigenvalues of that matrix are all negative. Okay. But you can also write it in this fashion. So this is saying what I just said, that it has to be less than 0, but even d square S by dv square should be less than 0. And but this combination, if you look carefully, is a determinant of that thing, but that has to be positive. Okay, so this is the statement of that the entropy is a concave function of its arguments. Okay, again, I'm just fixing on two variables because 2 by 2 I can show you pictures. In three-dimensional space I can't. It's more complicated. Okay. So here's an example. So what it says is that there are two directions. So this is what we'll call a concave, and convex means it's something like this. And saddle point is where one direction, this is a maximum in the green direction and it's a minimum in the blue direction. Is this clear? So these are the only three possible extrema in two variables. Okay. Higher dimensions, there are more possibilities, but here you can see. So is this clear what I'm saying? So I'm saying S should be a concave, entropy is a concave function, while what will energy be?
Convex.
Convex. Okay. So we check that. Okay. You can check that. Okay. So this is the, so again I'll pause here so that we can, so that you can ask questions. Okay. Everything is paka. Okay, good. Okay. So actually even in thermodynamics, there are several other thermodynamic potentials, and they are defined by a series of Legendre transforms. So again, the Legendre transform story is very nice if you look at it from the viewpoint of U. Okay, so if you remember, so dS was just T was du by ds, right? So this is exactly the standard Legendre transform, like, where you get F. So F is the Legendre transform of U, where we replace the variable S by the variable T. Okay, we get the Helmholtz free energy. Okay, next one is you go from U and go plus PV. The signs are important, but because you should get a state function. That's another way of checking this. So what you're doing is, so there's a pairing, like I said, S and T get paired here, V and P get paired here. So what you want to do is to replace V by P, and if you go back and see what is P in terms of U, you will see that it will be up to a sign. We can go back and see. It will be du by, yeah. There's a minus sign here, see? So it is minus du by dv. Okay. So what that does is it replaces the variable V with P, and this is called enthalpy. Okay. So again, we can ask experimentally, what is this kind of situation? So enthalpy is something which chemists use a lot, because in that setup, volume is not the control variable, but pressure is. Okay, so you're doing experiments. Again, there's a Gibbs free energy, which is double Legendre transform, where you replace S by T and V by P. Okay, so G of T, P, and N, and so this is the Gibbs free energy. Okay, there's another one called the grand function, which is phi, where you actually go ahead and do two Legendre transforms. You trade S for T, that is exactly like for Helmholtz free energy, and but keep V as a control parameter. But now what you're doing is you're replacing N with its conjugate partner mu, and you get this thing. So there are actually, you start from U SVN, there are actually 6 more possibilities. Okay, because we are looking at only 3 variables. So each of them you can make 2 Legendre transforms, so on and so forth. Okay, and I just want to pause here and hope you understand this statement. Okay.
I have a question.
Yeah.
Sir, if you take the case of H, it's a function of S, P, and N, but S does not show up in the expression there. So is it like implicit?
That's
it's
wrong,
only
because
U.
U is a function. U is a function. I didn't want. It takes too much space. U is a function of S, V, and N.
Okay. Right. Yes, sir.
All the U's are this. Good question. Okay. Anything else? Okay. So, and what does extensivity of S mean? So remember, I wrote it in a particular way. I wrote extensivity. Somewhere I don't remember now. Let me get to that. This thing. Okay, but there's a slightly different way of writing the same statement. Okay, can be written. So you can see all the variables which are being scaled are the extensive ones. U, V, N are extensive, and S also gets scaled. So what it says, so this is the same statement in some differential form. It says S du by ds plus V dV by dV plus N d by dV is equal to U. This is just statement of extensivity. So exercise, can you prove this starting from that other form that I wrote? You can write it with lambdas. You have to choose lambda, I think, to be some 1 plus epsilon, or I don't know. Okay, you can use whatever that is and see for yourself that this is what you would get. Okay, and so this is just a statement. One more way of understanding this is that S d by ds, you act on any polynomial, any monomial. Okay, if it has S power 5, S du d by ds is 5 times S power 5. Because you just pick out the power of this thing. So the scaling of that monomial is lambda power 5. So you can see that S d by ds, and any monomial will tell you the power of lambda which goes with it, the scaling. Okay. Similarly, V d by dB will tell you the scaling with respect to V and so on and so forth. Okay. So this is what this is. So now we can do one thing. We have this formula we have, but what is, so we can use now what is du by ds? It's 1 by t. What is du by dv? Looking at this, it's minus p. And what is du by dn? It is mu. You put all those in. So this will say s by t plus v du by ds is t. So it will say st plus v mu. Sorry, v times p. So you actually there's no need. So yeah, combining with this, which lets us do this, we get u equal to ts minus pv plus mu n. Okay. So you note that this is different from this expression. This is some infinitesimal thing. This says that u, the state function, is related to all these guys in this fashion. Similarly, you can go to the Gibbs free energy and you will see that Gibbs free energy is mu times n. Okay, so you might wonder, oh, okay, Gibbs free energy is a function of, it seems to be proportional to n. Where is the dependence on t and p? It is there. It is there buried in mu. Mu is a function of t and p. Similarly, if you go to the grand function, phi is just minus pv. So these are called Euler relations. Okay. Okay, so it's basically extensivity combined with the first law gives you Euler relations. Okay, so you can do it for all these variables. See, if you look carefully, all of them, u, f, h, g, phi, etc. are all extensive variables. Okay. So again, I will pause here for a second before I go to pictures. So we'll do this thing now in pictures. Okay. So it's useful to organize these various potentials. By potentials, I mean u, f, h, g, phi, phi 1, phi 2. There are no names for this. Okay. So it's useful to organize the potentials. For one component phase, we are considering there are just 3 independent variables and their conjugate variables. So we can make 8 different choices for the state variables. Namely, we can make 8 different choices. And we can represent them by the faces of the octahedron. So what is an octahedron? It has 8 faces, 6 vertices and 12 edges. And we will say that the edges represent Legendre transform. So if you're going from this blue guy to this light blue guy, you're going to make some kind of Legendre transform. Or if you're going like this, some one variable is being, you make a Legendre transform. So you can see this thing. So every face will be associated with one potential. Okay. And bunch of variables. 3, whatever are the 3 variables. So let's see what we get. Okay. So here, I'm following some convention. So blue edges are E to T Legendre transform. Red edges are V to P Legendre transform. Green edges are N to mu. Okay, so there are 3 Legendre transforms. So you can see that. So I'm showing here that we have a blue thing. Okay, so we have here we saw that if you start with entropy and you make a Legendre transform, you get the with E and T. So here I'm working. I've written the statistical mechanics version, not the. I'm working not in the U basis which I did here. Okay, but as we saw they are equivalent. So let's just see that. So here you can see when you cross from this phase to this phase, you get the Helmholtz free energy. The red ones are red edges are V to P. So we can ask what we get this way. So I just rotate this octahedron by 180 degrees, and so we get entropy and we get something which is a function of E, P, and N, and we can ask what is that guy. Okay, and that is why didn't I write that? E, P, and N. What is E, P, and N? Oh, okay. So I didn't give names for it, so that's okay. Okay. So let's just come here. Green edge is N replaced by mu, so that gives you the grand potential. Okay. Okay. So I just want to discuss one particular thing. So you can go from the Gibbs free energy, which is TPN, in green edge is N to this thing. You will get something which is a function of T, P, and mu. But there is no. I claim there is no such potential. Why is it? Okay, so
None of the variable describes the extensivity.
Exactly. Okay. So all the potentials are extensive and these are all intensive variables. So this particular, so even though this thing has 8 phases, there is one potential which will be 0. The other way of saying it is that there is 0. Okay. And you can see that. So we can go back and we can do it in this fashion. You go to G. Okay. So it's already a function of T, P and N. And then you do, what would be the Legendre transform? G mu N minus mu N. Okay, so that potential is 0 because that's the only way it can be. No function of it can be so. So that's not. So you can see that this statement G minus. So this can be written as G minus mu N equal to 0. So that potential is 0 if at all you want to exist. Okay, so that so really that's not something which is very useful. Okay, very good observation. Okay, that is this one. That is no. That is 0 if you wish. Okay, so here I just kept this slide for documentation purposes. How do we relate to statistical mechanics? And we did this last lecture. So we showed that by starting from Z we can take a definition of F and showing that it is concentrated around internal U. We showed that it's consistent with F equal to U minus Ts, which is what we had here. So this existed in thermodynamics long before statistical mechanics. So, okay. Okay. So I just want to do. I need only 2 more minutes. And so in magnetic systems, they consist of systems with magnetic moments, and you apply some external magnetic field, and they line up, and the magnetization is just the total magnetic moment per unit volume or whatever. Okay. And whenever you apply magnetic fields H, I use the symbol H here, but you can use B also. We'll discuss why there's a difference between B and H. And but okay, for us right now it doesn't matter. And the magnetic potential is just minus M dot H. A lot of people may have messed up this minus sign in the last assignment. So you can see that dW is just minus HdN. So we can easily define a fourth variable by just saying F prime is U minus Ts minus M dot H. Okay, and the response function here is the magnetization, and the second derivative is the magnetic susceptibility. Rather, this is wrong. What I want to say is that the force is the magnetization, and the response function is magnetic susceptibility chi. So that's a very, very interesting theorem, which goes back to Bohr and Van Leeuwen. Van Leeuwen was Bohr's supervisor. So it was that in classical statistical mechanics, the magnetization of any sample vanishes. And this is a very important point to remember. Classical mechanics cannot explain magnetic properties of matter. One needs quantum mechanics for that, as we will see in the rest of this course. Okay, so let's just take that there are a bunch of spins, many of them, and we'll focus on one spin and take Z power n or whatever. Okay, so what is Z? It's a free spin if you wish. It's just the semi-classical expression or classical expression. It's dx. You integrate over phase space, divide by h cubed, and then you do e power minus beta h. But for a particle in a magnetic field, you know the Hamiltonian, B is just written as del cross A. By the way, B need not be constant. Any B of x can be written as del cross A. And we know that the Hamiltonian is P minus Q, where is the Q is the charge, QA upon whole square upon 2n. So if you have a particle which is with charge Q, so let's not even, okay. So if you look at this, what you can see here is that this is, you can do the P integration first. Don't do the x integration, do the P integration. But what is the P integration? From the viewpoint of the P integration, A is just a number, so this is shift in a Gaussian. So if you do this integration, lo and behold, what you find is that the magnetic field disappears. And you get the same answer as if B were 0. Okay, so what we get is Z of TVB is independent of B. So classical statistical mechanics cannot explain non-trivial magnetization which we see. We see variety of materials, paramagnetic, diamagnetism, and so on and so forth. Okay, and even ferromagnetism, which is even more complicated. Those are all quantum mechanical. So magnetism is a quantum mechanical phenomenon. You need quantum mechanics. Okay, so even the idea of spin itself is a quantum mechanical object. Okay, so So you just can't start in terms of particles and just work out and show that the sample will be giving will show magnetization. So this is just something which is important to remember, because lots of books try to explain lots of things. Diamagnetism with some kind of Lenz's law, and actually wrong arguments are given. But we won't go through that path. We are in the 21st century. We don't need to do that, and so we will now move on to discuss magnetic systems and magnetization kinds of So you start with models of paramagnetism, and we will see what happens, and then we will understand ferromagnetism as well. Okay, so this is what we'll be doing next. So I'll pause here for questions.